We're going to continue on here, lecturing chapter 4. So a reminder, this will be exam 2 information here from this chapter on. That also means exam 1 is coming up on Wednesday. Yeah, so we're going to do it here during lecture. Again, something to write with, and a calculator is pretty much all you need, and all you'll be given, a periodic table as well. So again, this will be for exam 2. So let's talk about chapter 4. First, we're going to talk about sort of compounds and their formulas. And we talked about compounds previously. And remember that a compound is always a combination of 2 or more atoms. The key, right, is that there has to be some different elements involved for that. And again, that is slightly different than the basic definition of a molecule that we talked about, which is really just a combination of 2 or more atoms together. And remember, for a molecule, that could be 2 or more atoms of the same element, which would actually make it an element rather than a compound. Or it could be 2 or more atoms of different elements, which would make it a compound. So again, that compound aspect of it is has to have at least 2 or more elements sort of involved. And something like water, obviously, is formula there, H2O, is obviously a combination of both hydrogen and oxygen here, which would make it a compound. Again, it would also make it a molecule because there definitely is 2 or more atoms together. Once again, as we might have touched upon earlier, it would not make it an element, obviously, because there's hydrogen and oxygen, 2 different elements involved. If you had something like H2 just by itself, once again, it would be 2 atoms together, which would make it a molecule and would make it an element, as there are only atoms basically of hydrogen present in that particular case. When we do write the chemical formula, as it says there, we do use the symbol for each element and a subscript for our guide for how many we have. And it does go to the element to the left of the number is what the number refers to. And in most cases, like we see in chemistry, pretty much if there's nothing written, it again is assumed to be a 1, not a 0. So if you see nothing written, it's assumed to be one of those things. So in the case of the oxygen, we would have 1. When we write our symbols, a couple reminders that they could be 1-letter symbols, like potassium here, which is K, and it would be a capitalized letter. So if you have a 1-letter symbol, it should always be capitalized. If you have a 2-letter symbol, thank you, it will be capital of the first one and lowercase of the second, which in this case would be cobalt. If we were to, again, write capital letters for both of them, capital C and capital O, a reminder that would not be cobalt, which is an element. That would be carbon monoxide, which is very different than cobalt. So this would imply 1 carbon atom and 1 oxygen atom, which would be carbon monoxide. So it's always important when you write those symbols to always capitalize and then lowercase if it is a 2-letter symbol. Because again, if you kind of capitalize them both, you may be writing something you're not really intending to write. Any questions on that there? So as we just talked about, some other examples, CO2, which is carbon dioxide, nothing written. So 1 carbon, 2 oxygens, nothing written, or ammonia, 1 nitrogen, 3 hydrogen atoms are basically attached there. In the case of ammonia, it looks something like this: 1 atom, 2 atoms, 3 atoms, 4 atoms. Again, that would definitely be a compound, as we have 2 or more atoms. And we also have 2 or more elements obviously involved as well. All right, so why don't you take a couple minutes here and write the proper formulas for each of these. Okay, let's take a look. So here we're looking for a molecule that contains 6 carbons. So we'll go with C6. And 6 hydrogens, so H6. So we got a little bit like that. Again, subscripts for our numbers of each of those guys that are present. We have a compound that contains half as many calcium as chlorine. So if I just have one calcium, that would mean half of that. I would need twice as much Cl's there to do that. Give me CaCl2. And lastly, here we've got equal numbers of sodium, Na, and nitrogen. And we have 3 times as many oxygens. So since we have one of each of those, 3 of those will give us a little NaNO3, or sodium nitrate in this case. Any questions on any of those there? Okay, so what we're going to talk about next is really the atom, and we're going to talk about some different experiments to help us understand sort of the structure of the atom and different components of the atom. So let's start with the atomic theory here. So a lot of the idea behind atoms started a long time ago with the idea that we have these very small, indivisible, indestructible sort of particles, which are known as atomos, which is sort of a forerunner to our atoms. And around the turn of the 18th century, there was this idea that most of the natural materials were either mixtures of pure substances. Remember, as we talked about, when we talked about pure substances, it can either be an element or a compound. And there's this idea of the law of composition, which basically means that regardless of where a compound comes from, it pretty much will always have sort of the same mass of elements to each other. So for example, no matter where you would pick up water, there's definitely 2 hydrogens and 1 oxygen involved. Each hydrogen, it's about 1 gram or so. So that's about 2 grams of hydrogen, and each oxygen is about 16 grams. So if we divide it by 2 here, basically for every 1 gram of hydrogen, we should have about 8 grams of oxygen, no matter where you get the water from. The water costs more money, packaged differently. It should always really end up in that sort of mass to mass sort of ratio of how many grams of hydrogen per oxygen. And this led to really the first sort of important atomic theory, which is Dalton's atomic theory. And Dalton's atomic theory is correct in a lot of aspects. But as we talked about when we talked about theories, remember that they can be sort of revisited, revised, and maybe later found that not all parts are correct. And that's also the case that happened with Dalton's atomic theory. So a little about John Dalton. He had good talent for math and science. He kept weather records every day. Kind of woke up, wrote down the weather. He never married, surprisingly. But the most important thing, really, as you leave this class, is he liked to go bowling on Thursdays. So that definitely will be on the exam, every exam. So don't put any other day. Don't put like Fridays or cosmic Saturdays. It definitely would be Thursdays. And besides going bowling on Thursdays, he's clearly known for really a theory that helped define what atoms are. So let's take a look at some of his important parts of his theory. Talk a little bit about what is still sort of correct and what is incorrect. He said that basically elements are composed of extremely small particles called atoms, kind of indestructible sort of particles. He said that all atoms of a given element are identical. They have the same size, mass, and chemical properties. He also said atoms of different elements are different from one another. He said that compounds are composed of atoms of more than one element. A chemical reaction basically only involves the sort of rearrangement, recombination of these atoms. We don't really create nor destroy any sort of elements along the way in a normal chemical reaction. And that's sort of the law of conservation of mass. Basically, what we start with and what we end with is really the same element. So if we started with, again, 6 carbons on the left-hand side of the arrow where we start, we should end with really 6 carbons on the right-hand side of the arrow. They may be in different compounds on the right-hand side of the arrow, but since 6 carbons each one has a mass of 12 grams, they would have the same mass on the other side. So we have that conservation of really the elements and also the mass. A couple of things that were found to be later not so correct. This idea that atoms are indestructible, that is not so correct. And really, this part here was found not to be so correct because of the presence of what is known as isotopes. And isotopes are the same element, but they have different masses. And as we'll talk about, the reason they have different masses is because they actually contain different numbers of neutrons. So even though they are the same element, they obviously cannot be identical to each other, the atoms of all those, because there are some that are heavier, there's some that are lighter because of the different numbers of neutrons that are present. So those two things are really the part of Dalton's atomic theory that do not hold up. Indestructible, you can sort of, for example, change an element in a reaction, but it would have to be a nuclear reaction. So in a nuclear reaction, you could change what's inside the nucleus, the protons, the neutrons, and actually what you start with and what you end with is always completely different in terms of elements. In terms of chemical reactions, like we talked about in this class, that does not happen. So what we start with and what we end with in terms of the elements are always the same, because chemical reactions only involve electrons and basically breaking and making bonds. It has nothing to do with the nucleus, which is really what is responsible for what elements you have. So because in a normal chemical reaction, you pretty much do not play with the nucleus, you just play with the electrons and the bonds. We have that sort of conservation of elements as the reaction takes place, which is why when we use a chemical equation, as we'll talk about, it does need to be balanced. We need to have the same number of elements on each side of the arrow. But he was correct in the aspect of atoms from different elements are different. So a copper atom will be different than an iron atom. He's also correct that compounds are more than one element together, and also correct again that chemical reactions only involve really the rearrangement of those electrons and bonds. Any questions on that? So you do need to know, obviously, the different parts of Dalton's atomic theory, what's correct, what's maybe incorrect. Any questions on that? Okay. So Dalton sort of pictured atoms as collection, or compounds as collection of atoms together. And there is sort of a relationship. For example, here, if we look at just two elements, nitrogen and oxygen, nitrogen is about 1401 grams. Oxygen is about 16 grams, which means that if we divide both of these by 1401, that will give us obviously a 1 here, and that will get us, if we do 16 divided by 1401, roughly 1.14 grams of oxygen for every basically 1 gram of nitrogen that we've put in there. So in this relationship, when nitrogen and oxygen comes together, for every 1 gram of nitrogen, we should have about 1.14 grams of oxygen. And in this case, we see a relationship here. We have our nitrogen, and we actually have twice the amount of oxygen. So if we have twice the amount of oxygen, for that, we would expect to be basically 2 times 1.14 grams, which gives us something like 2.28 grams of oxygen present in this case. Yeah. It's actually from the periodic table, so that's the atomic mass. Those are numbers that you'll see underneath the symbol on the periodic table. And it's basically how many grams there are in 1 mole of those. And we'll talk about it a little bit later on in this chapter, next chapter. But roughly, those are sort of the grams of each of those atoms per mole. Other questions? So if we look at that, if we did that for our NO2, we would have, again, about 1401 grams for our nitrogen. We would have 2 times 16 because there's 2 oxygens, gives us about 32 grams of oxygen. So if we divide this by 1401, so we take 32 divided by 14.01, we get roughly there are 2.28 grams of oxygen that we would expect. So that is sort of the relationship, and what he basically visualized was that atoms come together really in sort of whole number, sort of multiples of each other as to, if you took the grams of one element versus the other, you can make a prediction as to how many grams of the other element you would have in that particular case. Any questions on that? So you could also do the same thing for this. This is a little bit different since we have two nitrogens. So instead of 1 gram of nitrogen, if you divide this by 2, you would basically have about 0.5 grams of oxygen per nitrogen. And that's what you would get if you kind of do the same sort of math on that guy. So let's talk a little bit then about the structure of atoms. And again, we're going to talk about some important experiments along the way that helped us sort of really delve into the nature of the different parts of the atom. So a couple of things based on Dalton's atomic theory, the atom was really defined as the basic unit of elements that could come in contact. Although atoms are extremely small, it was found that they do really possess an internal structure, and these are sometimes referred to as subatomic particles. So they're made up of even smaller particles, even though they're really small. And these are our big three here. These are our protons, which, as we'll talk about, has positive charge. That's our electrons that have a negative charge. And that's our neutrons, which have no charge, basically. So, although atoms are really, really small, they're really comprised of even smaller sort of internal structure as to what makes them up. So we're going to talk about some experiments that helped us understand each of these different sort of particles and maybe sort of where they are in the atom. So the really first one that we're going to look at is our electron, which obviously again has a negative charge. And really some of the most earliest work done on electrons and sort of an understanding of electrons came about with the invention of what's referred to as the cathode ray tube, or the CRT. Cathode ray tube, a sort of picture of it is here, and how it works, and really a lot of sort of the experiments that were done to understand the nature of the atom really took advantage of the idea that these internal subatomic particles charge. So in chemistry, as we might have talked about, there is this idea of basically opposites attract. So anything with a positive charge is attracted to anything with a negative charge. And it also is dependent on the actual value or magnitude of those charges. And what I mean by that is if you have something that's a +1 and a -1, it definitely is attracted to each other. If you have something that's a +3 and a -3, it's actually going to be stronger attracted to one another than the +1, -1. So the level of attraction between things that are opposite in charges actually increases with increasing the charge size. And that also means another important idea is that things will repel one another when they are the same charge. So when we have something that is positive near positive, not so good. We have something that is negative near negative, also not so good. But again, here, opposites there do attract. So a CR2 T tube here, or cathode ray tube, takes advantage of that idea, and we could take advantage of that idea by using something like an electrical field or even a magnet to that extent as well. And basically in a CRT tube, we have this beam of really negatively charged particles, and we have a negative side and a positive side here in terms of electrical field. And that means that these negatively charged particles are going to head towards the positive side of that electrical field. It's going to move away from the negative side of the electrical field. And you may be familiar with CRT TVs or computer monitors. If you've ever seen an older TV that has like a back on it, kind of comes out, or a computer monitor that kind of comes out like that. Not this one, obviously. So you could Google it if you haven't seen it, but that is basically a CRT monitor. They used to call them CRT monitors. And inside those old TVs is basically a CRT sort of picture tube that's shooting these type of things at you. So when we look at a CRT tube here, basically what happens, as I mentioned, is these negatively charged particles are going to be drawn towards the positive side of the plate, away from the negative side. And a lot of times what they will do is put like a fluorescent material at the end where sort of the beam is heading, and you could actually kind of see and pick up as it will sort of glow when it hits that material, and you'll be able to see where the beam's actually hitting. So as I mentioned earlier, that is what a lot of people have done to take advantage of these guys that have particles or charges. And there's really kind of three types of radioactive particles that were used a lot in a number of these experiments. And they are alpha particles. And those are basically positive charged particles, radioactive particles. There's beta particles, which are basically negatively charged particles. And there are gamma rays, which basically have kind of like no charge associated with them. So they are sort of equivalent, if you will, or sort of related to, kind of similar to protons, positive charged particles, negatively charged particles, or like beta particles. And gamma rays, which have no charge, are very similar to what we see with neutrons. And that's what we see here when we look at the effect of when you send a charged particle through an electrical field or a magnetic field, which has a north pole and a south pole. It kind of works very similar. So if you did have a electrical field sort of set up and you shot a particle and it sort of bent towards the positive side of the electrical field, you would know that that particle has what type of charge? Should have a negative charge, right? Opposites. If you shot a particle and it sort of bent towards the negative side, you would know that that guy is a positive charge. And if you actually shot a particle and it kind of went straight through, really not bending either way, imagine that straightish line there, that would have something that has no charge, as it's obviously unaffected by the electrical field or even the magnetic field because it does not have a charge. So again, these alpha particles, beta particles, and gamma particles are radioactive particles that were used in a lot of these experiments because they do have charges similar to those charged particles that we see that are electrons, protons, and definitely moving as the magnet comes near it, which would imply obviously it has a charge as it's affected by the magnetic field of the magnet coming through it. So she mentioned picture tubes. I know it might be hard to believe, but you know, when your TV went out, you didn't go to Costco and just buy a new one. You called somebody to your house. They opened up the back of the TV and they fixed it, believe it or not. Yeah. And those old TVs did have those picture tubes, which were kind of like the CRT tubes in it. I know you could Google it again if you're not sure. All right. So one of the earliest sort of experiments and one of the important experiments to help us understand really electrons was done by a guy named Thomson. And he did use these cathode ray tubes to really study the electrical and magnetic forces of these negatively charged particles. And what he was able to do, there he is with his cathode ray tube right there. He was able to figure out the charge to mass of an electron. And he was able to figure out the charge to mass of an electron being that number right there. So Thomson able to figure out the charge to mass of an electron, and the charge is represented by a coulomb, so that is a unit of electrical charge, and grams is obviously the mass, so that is the charge to mass of an electron. And that was a very good sort of step forward in the understanding of electrons. And really the next kind of important experiment that sort of complemented Thomson's experiment was one that was done by Millikan. And Millikan did what is referred to as the oil drop experiment. And what he was able to do is take oil droplets, send it into this chamber, and basically atomize them. And as a droplet of oil would start to drop, it would basically gain a charge. And what he was able to do in this chamber was he had an electrical field, and he was able to basically adjust the electrical field in such a way that pretty much the oil droplet could just hang there, basically. It didn't go up, didn't go down. He was able to really dial in the charge on it, basically. And from that, he was able to figure out the actual charge on an electron. So that's the oil droplets, again, adjusting the electrical field, allowing the oil droplet to really just kind of hang there. And the most important thing that came out of this experiment was he was able to determine the charge of an electron, which is this number right here, Coulomb, again, a unit of electrical charge. So this experiment and Thomson's experiment are really important in understanding the electron, because we have Thomson, who figured out the charge to mass of an electron. We have Millikan that figured out the charge of an electron, and really using both of that piece of information, or those pieces of information, the mass of an electron was able to be really determined. So these two experiments really led to the understanding of both the charge of an electron and also, more importantly, the mass of an actual electron. So if we were to do that math using the results of these experiments here, we basically take the charge divided by the charge, the mass of an electron. The charges cancel, grams come to the top when we divide, and we're able to determine that the mass of an electron is 9.09 times 10 to the minus 28 grams. That is a small number, large number? That is a really small number, right? We're going 28 places to the left, putting a bunch of zeros down, right? It's going to make it a really, really small number. So the first couple of things you need to know in terms of these experiments is Thomson's experiment with the CRT tube, what came out of it, Millikan's experiment with the oil drop, what he did, what came out of it, and really that using both of those experiments, the mass of an electron was able to be determined. On that so far. Okay. So now that we sort of know that atoms contain electrons which are negatively charged, that leads us into really the other sort of components of an atom. And it definitely was believed a couple of things about atoms at this point. They were believed, obviously, to contain electrons which are negatively charged. And it was also believed that they were electrically neutral. So if an atom contains negatively charged particles, but they are neutral, that would imply that there has to be some type of positive charge there to balance everything out, right? To make it neutral, not have a charge. So obviously what they were looking for was this idea of sort of the positive charge of the atom, maybe where it is or how it is sort of there in an atom. So this led to a sort of early model of the atom that was proposed by Thomson. And this is sometimes referred to as the plum pudding model. And basically what Thomson said was he felt that the atom was this uniform of positive charge. So we got this sort of positive charge that's really spread out over the entire atom. And embedded inside this positive charge were our electrons. So embedded inside here were our electrons. And the plum pudding is the English dessert of pudding and raisins. So like the pudding kind of spread out, it's all the positive charge, and electrons sort of embedded inside like the raisins. And the other major part of this model of the atom was that he felt that most of the mass of the atom was the electrons. So Thomson's early model, the plum pudding model, which you do need to know, is a sphere of positive charge where we have electrons embedded inside, and electrons make up most of the mass of the atom. Any questions on that there? Here's a much prettier picture than that if you can find it in your book, but you get the same idea. We have this cloud of positive charge, electrons embedded inside, and again, in this theory here, most of the mass of the atom are those electrons. And this was really sort of the accepted model of the atom until further experimentation was done. And the next really sort of major experiment along the way to the understanding of the current model of the atom was one that was done by Rutherford. And Rutherford, a guy by the name of Geiger and Marston, but usually attributed to Rutherford here, did what is referred to as the gold foil experiment. And much like the name implies, he took alpha particles that we talked about, these alpha particles again being our positively charged radioactive particles, they're really helium. And he basically shot these particles at pieces of gold foil, which are atoms, with the understanding of sort of the plum pudding model of the atom. So what he anticipated or thought of was, again, we have this atom of positive charge. We have these negatively charged electrons sort of embedded inside. He's going to take these positively charged particles and basically alpha particles and shoot it at him. And what he expected to sort of happen was when he shot them, he expected, because they are positively charged, shooting at something that's positively charged, but they're heavy and they're moving really quick, he expected them to be able to sort of punch through that positive charge that's spread out, but there should be some deflection. So, for example, if this was my atom and this was positive charge spread out all over this, if I held this side really tight, somebody else held like this side really, really tight, and if this was sort of like our positively charged guy going through, if we shot this pin at it really fast and hard and it was really tight, it would be able to probably punch through, right? But as it went through, there probably would be some deflection as it kind of went through that positive part of it. And that's actually what he expected to happen. And he was really surprised when he did it. When he did this experiment, he found that actually most of them passed through no problem. So most of those alpha particles passed through, they were undeflected. He also saw, though, that every now and then, he saw most of those, just saw them pass through no problem. But every now and then, he would see these alpha particles basically bounce off at angles, maybe even come back to its source. And that was really surprising to him because of the previous version of the model of the atom that he thought of was sort of correct. So if we think about some of these things, if these alpha particles sail through with no problem and basically did not bounce off anywhere, what did they hit? Did they hit anything? They pretty much did not hit anything, right? So if we go back to my example, my pen, if I take my pen and throw it without the paper there, there's nothing in the way, right? It's just going to fly through, right? Undeflected or anything like that. So a lot of these particles found really nothing in its pathway, right? Because it was able to just shoot by really easily undeflected. But we did see every now and then that these alpha particles were spread out and deflected at wide angles. So in order for an alpha particle to bounce off at a really large angle, and since alpha particles are positively charged, what type of charge thing did it have?
By the low mass electron. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So as we can see in that little animation, most of those alpha particles, no problem, came straight through. And as we talked about, pretty much hit nothing, pretty much that empty space. And we see these alpha particles, though, scattered at these large angles. Some would come back. As you mentioned, it did have to hit something that was very, very positive. So if we sort of think about the version of the atom, which was our plum pudding model, we sort of have to step away from that plum pudding model and go, not so correct. And if we instead have having a positive charge spread out over the entire molecule, if I take my positive charge and I fold it, which can easily be done apparently, you can just fold that. You fold it how many times there? Like 7 or so before. Can't fold anymore. But now instead of my positive charge being spread out all over the actual atom, if this is all my positive charge, right, centralized in one location, and I shoot my pen at it, you can see definitely my pen is not going to go through it. It hits something of the same type of charge, is why we see those guys really reflect off in a large angle. So basically, they had to kind of go back to the drawing board and kind of go, well, this plum pudding model proposed by Thomson, again, not so good. So we do have to kind of come up with a better model of the atom. And basically, and again, here on the left is what they thought would happen. On the right is really sort of what they saw happen. What they said was basically the atom is mostly empty space, and that accounts for pretty much why most of those particles had no problem coming through. So our atom is mostly empty space. As we just talked about, it had to have a very dense positive core, which they called a nucleus. So we got this nucleus, which is a very densely positive core, which were later found to be the protons being those positive guys. And in about 1932, neutrons were also found to have no charge, also found in the nucleus. And our electrons are out in that empty space, basically flying around, sometimes referred to as the electron cloud, where they're kind of flying around in. By the way, do electrons travel in pretty circles? They do not actually. They travel very randomly about the nucleus, as we'll talk about. Was known again as that Heisenberg uncertainty principle, is the idea that the more you know about how a particle like an electron is traveling, the less you know about its actual location, and vice versa. So the best we could see is there's a good probability of finding an electron in a particular spot within the atom. And we know, just logically speaking, should there be attractions between the electron and the nucleus? Should there be an attraction between those two things? There should be, because again, our nucleus is basically positively charged. Our electrons are negatively charged. So that is what, kind of keeps them there. It's also why not all the electrons just take off, right? In an atom, they have that sort of string is sort of holding them to the nucleus. It's also why we'll talk about in later chapters why, for example, only certain electrons are involved in things like bonding. And those are referred to as valence electrons, ones in the highest energy level, furthest away from the nucleus, because those electrons furthest away from the nucleus is not going to be held as tightly as those electrons which are closer to the nucleus. So those electrons that are closer to the nucleus, are sometimes referred to as core electrons, are held a lot tighter because they're just right up front there next to that positive charge of the nucleus. There's a really strong attraction. And as you get a further distance from the nucleus, there's less of an attraction force as you would feel closer to it. The other major difference between Thomson's model and really the current model of the atom is, in Thomson's model of the atom, it was thought that the electrons were responsible for most of the mass of the atom. But here it is the nucleus that is responsible for most of the mass of the atom. So this is sort of the currently accepted model of the atom, mostly empty space. Within that empty space is where we have our electrons flying around. We have a very dense positive core, which is our nucleus, where we have protons, which are positively charged, and neutrons, which have no charge. And again, most of the mass of the atom is made up of that nucleus. Any questions on that there? So you do need to know Rutherford's experiment, what he did, yes, and what he thought was going to happen, what happened actually, and obviously the moving away from Thomson's model of the atom to the current sort of modern version of the atom, which is our mostly empty space nucleus model. Any questions on any of that there? So this is just a little table, really, of those experiments we just talked about, in case you want to just reference it. That information on the table, obviously, you should know pretty much what came out. So as I mentioned, that positively charged nucleus does contain, and it was found through experiments, that a proton has a mass of 1.67 252 times 10 to the minus 24. Remember that the mass of an electron was 909 times 10 to the minus 28 grams. So once again, this number is actually larger. And a reminder that when you have negative exponents, the smaller negative exponent is actually the larger number. Because minus 24 means I'm going 24 places to the left with zeros. Minus 28 is 28 places to the left with zeros, which makes it a smaller number. So it was found that basically a proton is about 1,840 times heavier than an electron. And that also helps with Rutherford's idea that the nucleus is most of the mass of the atom, because the protons are found in the nucleus, and each proton in there is about 1,800 times heavier than any electron that's flying around. And that makes sense that the nucleus would then be most of the mass of the atom rather than the electrons. Now, at this point, scientists really perceived that the nucleus is comprised of most of the mass of the atom, but it actually is a very small volume, which, explains why, not a lot of those alpha particles maybe bounced off in all those directions. So you could think of the atom as kind of being like the size of a big football stadium, if you will, or the Superdome, if you've ever been. Big stadium, you sit on your seats, you feel like you're going to fall over just sitting. But the Superdome or a big football stadium, and like the nucleus is like a marble on the 50-yard line. So, a bunch of empty space where those electrons are traveling, really densely positive core where that nucleus is. So, as I mentioned, we got our protons, we got our electrons, and there was always a belief that there was really another particle basically in the nucleus. And it wasn't really until 1930s that James Chadwick basically discovered through experimentation, basically the existence of what he called neutrons. And what he saw was he did a lot of work with beryllium, and what he saw come off of these sheets of beryllium were radiation that resembled gamma rays. And gamma rays, if you remember, are those guys that have basically no charge, just really pure energy. So he called these guys neutrons, which again are also found in the nucleus. And neutrons have a mass of 1.67495 times 10 to the minus 24. And if you remember, the proton was like 1.672 something times 10 to the minus 24. So the neutron just takes out the proton of how massive those three sort of subatomic particles. It is the neutron followed very closely by the proton, and then the electron much, much smaller in terms of mass. It is the heaviest, I guess is the better way to put that. Heaviest, and the electron is the lightest of those different sort of particles. So you definitely need to know neutron is the heaviest, followed very closely by the proton, and electron being the lightest of all three of those guys. Any questions on that there? So again, that also sort of reinforced the idea of the nucleus being most of the mass of the atom, because both the proton and the neutron are about 1,800 or so times heavier than any electron. So again, our proton positively charged nucleus, electron negatively charged out from the nucleus in that empty space. And our neutron has no charge in the nucleus, right? And our super close masses for each of those. But again, the neutron just barely beating out the proton in this case. Any questions on that there? So obviously you need to know where these particles are found and their charges, and again, which one's the heaviest, the lightest, and so forth. So here is a picture of sort of what an atom looks like. And again, this sort of pinkish color here is that empty space, really sometimes referred to as the electron cloud. And it's really what's referred to as a probability sort of map. And you could kind of see the distinction on the screen a little bit. Darker areas is a greater probability of finding an electron in the atom. Kind of lighter colors as you kind of vary out is less of a probability. Again, we don't know exactly where an electron is at any given time, but that's what the colors are. We could kind of see the darker colors is near the nucleus, which again does make sense as we have that positive charge of the nucleus. So there should be a pretty high probability of finding that negatively charged electron flying around somewhere near it. And as you kind of fan out from it at a greater distance, the probability starts to decrease. Doesn't mean you cannot find an electron there, but there's a less of a chance than you would be closer to the nucleus in this case. All right, and here's just again the relative sizes versus an electron. And we can see these guys are much, much heavier than any electron. All right, so the nice thing about really the chemistry of atoms and normal chemical reactions, as we've been talking about, is the idea that they really do come from just the interaction of the electrons. And since we really don't do anything with that nucleus in a normal chemical reaction, we do keep the elements, we maintain the elements, so we just get that rearrangement of atoms as we go from reactants to products in a chemical reaction. And it does make sense if you think about electrons are involved in atoms with one another as those electrons, and that's really the basis of all types of bonding. Ionic bonding, covalent bonding is that interaction of those electrons making breaking bonds as we go from reactions to products. So let's talk about some other important aspects of an atom, and that is the atomic number, the mass number, and isotopes. So starting with the atomic number, which is sometimes abbreviated with a Z. The atomic number is the number of protons there are in the nucleus of an atom. Now, if you have a neutral atom, and since as we just talked about, there's really only three particles. There's protons, which are positively charged. There's electrons, which are negatively charged. And there's neutrons, which have no charge, which obviously cannot affect the charge of anything. So in a neutral atom, all the positive protons would have to be balanced out by all the negative electrons. So if you know the atomic number, which is the number of protons, you will also know the number of electrons if it is a neutral atom. There is an important distinction, though. If you're asked a straight up question of give the atomic numbers definition, it is only the protons. So the definition of atomic number is the number of protons there are, and only the number of protons. The information you could get from that, again, is if it is neutral, it will also tell you the electrons, but that is not part of the definition of atomic number, strictly just protons. So the atomic number, if we go to the periodic table, is our friend up there, up on top of the symbol, is that number that's up there. So for hydrogen, we see 1. For nitrogen, as we see there, it is 7. And we see something like carbon, it is 6. Right about there. So if we look at nitrogen, nitrogen should have 7 protons, which are positively charged. And if it is a neutral atom, it should also have 7 electrons, which would then give us an overall charge of 0 when we have 7 positive things and 7 negative things, giving us that overall charge of 0. When you look at the periodic table and you look at those numbers that are above the symbols, do any of the numbers repeat? There's absolutely no number on top there that repeats. And that is a really important aspect of atoms. That means every single element has its own atomic number, which again is the number of protons in an atom. So you would never find a nitrogen with an atomic number of 7 or 7 protons, because the one that has 7, I'm sorry, you never said, I said that backwards, try again. You'll never find a nitrogen atom with 5 protons, because the one that has 5 protons is boron, right? Up there on the periodic table. So boron is number 5, and it should have 5 protons. Nitrogen needs to have 7. So this also tells us out of protons, electrons, and neutrons, the most important subatomic particle that helps us determine what element it is which one? Is the proton. So if you change the protons, you change what element it is. And that again is why in a normal chemical reaction, when we only play with electrons, we don't touch protons. We always have the same elements that we start with and end with because we don't do anything to the nucleus. We don't change protons. We keep the same elements from beginning to end. That's also why when you take 1B, you do the nuclear chemistry chapter. When you do a nuclear reaction, that's pretty much all you do is change the protons to neutrons, neutrons to protons. So you mess with the nucleus all the time in nuclear reactions. And that is why you do not have that sort of conservation of elements. But again, in this class, in 1A, we deal with just basically chemical reactions. So we always have just electrons involved. We never touch the protons. So we always have the same elements that we start with and end with. But it does change if you do play with the neutrons. Any questions on that? So clearly, if you know the number of protons and the atomic number, which is basically the exact same thing, and you have a periodic table, you should know exactly what element you're dealing with by just simply finding that number on the periodic table. Another really important number is the mass number. And the mass number, which is sometimes abbreviated as an A, is the number of protons and the number of neutrons there are in an atom. And these two numbers are really important together. If we take our mass number, which is our number of protons plus our number of neutrons, and we take our atomic number that we've been talking about, which is our number of protons, and frankly, if we subtract the two, protons cancel, gives you the number of neutrons. So if you take the mass number minus the atomic number, that will give you the number of neutrons there is in an atom. Every single element will have protons, electrons, and neutrons, except hydrogen. Hydrogen only has a proton and an electron. No neutrons. That gives hydrogen some unusual properties, but everybody else will have all 3 of those particles, but hydrogen does not have a neutron, just a proton and an electron. The mass number, the atomic number, the number of protons, electrons, and neutrons, they all should be positive whole numbers. So that's a really important thing to remember, more so the whole number part of it. So that brings up the question of, if I roll my periodic table here and I roll with the number on the bottom, are these the mass number? Or those are the mass numbers? They are not the mass numbers, right? These are actually the atomic mass, which is different than the mass number. If you look at the periodic table at that number that's underneath the symbol, pretty much there is no whole numbers, and all those things need to be whole numbers: protons, electrons, neutrons, mass numbers, atomic numbers. You will have enough information in these type of problems to be able to calculate all those things. Do not take the number from the periodic table on the bottom there and write it. And if you see yourself doing that and you're writing it with a decimal, there's always multiple people that do it. Just put the X yourself on those questions because it's going to get an X. Yeah. And what confuses people is very commonly the mass number and the atomic mass you see on the periodic table are very close numbers. So almost like people think, oh, they must just like rounded the number, and that's why, you know, it's a whole number and stuff like that. So they are actually not just rounded versions of each other. They are different. They are made up kind of based on the same kind of things: protons, electrons, and neutrons. But as we'll talk about in a later chapter, the atomic mass is actually found by taking the average mass of different naturally occurring isotopes. And again, the very common confusion is, like I said, a lot of times the mass number and that number is like a super close number. But again, you do not get the mass number from the periodic table. Any questions on that? So that brings us to isotopes. And as I mentioned before, isotopes are really the same element, but they have different masses. And the reason they have different masses, again, is because they have different numbers of neutrons. And again, that was one of the things from Dalton's atomic theory that was incorrect. Remember, he said that basically all atoms of the same element will be the same. And again, the existence of isotopes means that that's not so correct. So for example, here we have hydrogen, which has 1 proton and no neutrons. We have deuterium, which is sometimes referred to as heavy hydrogen, has 1 proton and 1 neutron. We have tritium, which is like the radioactive version of hydrogen, has 1 proton and 2 neutrons. There is a very common way that we represent isotopes when we write them. We use the chemical formula, again, capitalized if it's 1 letter or capitalized in lowercase if it's 2. Mass number, top left. Atomic number, bottom left. So if we were to write the symbols for all 3 of those guys there, we'll start with hydrogen. It has 1 proton and no neutrons. So for example, if you weren't sure what hydrogen's symbol was, it is the 1 proton, means it has atomic number 1. So you would go to the periodic table and you would find number 1, which is hydrogen, and that is what you would write. Its atomic number would be bottom left, which is 1. Remember that the mass number is protons and neutrons, which in this case is 1 plus 0 is 1 for our mass number. And that would go top left. So that would be our symbol for hydrogen. Top number, mass number. Bottom number, atomic number. And to figure out neutrons, top number minus bottom number. 1 minus 1 is 0, gives you 0 neutron. Now, this is helpful to know the idea about atomic number, because when we get a name like deuterium, doesn't sound like hydrogen at all, but we know it is actually still hydrogen because it also has 1 proton. So again, if I went to the periodic table, I would see number 1 is still H. So we would use H. Once again, the atomic number is 1. In this case, the mass number would be 1 plus 1, which is 2. So we'd have 2 up on top and 1 on the bottom. And that would be our symbol for deuterium. Again, if we took 2 minus 1, that would give us 1 as the number of neutrons in this case. Once again, tritium doesn't sound very much like hydrogen, but I do know it is hydrogen because it has, again, 1 proton, which means, again, when I go to the periodic table, it is still hydrogen that I'm going to use. And now in this case, we have 2 plus 1, which is 3 for our mass number. So this is hydrogen symbol, deuterium symbol, and tritium symbol with both the mass number and the atomic number. And again, although they all 3 have different names, they're all still hydrogen because they all have 1 proton. So as long as we didn't change the proton, the 1 proton in this case, they will all still be hydrogen, and they are all isotopes of each other, the same element. They have different masses because, again, they have different numbers of neutrons. Question on that there. Now, another way that sometimes isotopes are written is like this. Cu64, for example. Copper 64, which is a radioactive version of copper. That 64 would be what number, do you think? 64 is it's actually the mass number. And I know that because if I go to the periodic table and I look at copper, above it is 29, which would be the atomic number, right? So again, the periodic table is really helpful, obviously. If you're not sure what that number would represent in the right direction. That means if I write the symbol the other way, copper 64 would go up on top. 29 would go on the bottom, and it is neutral. So the number of protons in this case would be 29. Our number of electrons in this case should also be 29. That gives us a grand total of 0 for the charge. Our number of neutrons in this case would be our mass number, 64 minus 29. Gonna give us like a 35, I think, in this case, if I'm not mistaken. Any questions on that there? If you want me to try some here. So for each of these, determine the number of protons, electrons, and neutrons there are. One here is cobalt. Again, the top number is our mass number. Bottom numbers are atomic number. And again, our CO, which is cobalt, it is the atomic number, which will tell us the number of protons. And in this case would be 27, basically positively charged protons. We know that this is neutral because frankly, we do not see anything written here. So if it did have a charge, that is where we would actually see it. So because it is neutral, we should have an equal amount of negatively charged electrons. That means, again, our number of electrons in this case should be 27. Again, 27 positives and 27 negatives gives us no charge overall. Our number of neutrons is going to be our mass number, which is 60 minus 27. Looks like a 33 in this particular case. Any questions on that one there? Taking a look at the next one, which is chlorine. Once again, we see no charge. And we're going to first look at the atomic number, which will help us out. If we weren't given that number, we could go to the periodic table and look up Cl and see what it says. And again, if we did that, we would see the 17 there. So again, if you're not sure, you could always use the periodic table to help you out. That would tell us in this case, we do have 17 protons. Because it is neutral, once again here, we would need an equal number of electrons to get us to no charge. And our number of neutrons in this case, is that 37? Minus 17, which would get us 20 in this case. Any questions on that one? Lastly, U is uranium. And once again, no charge. Looking first at our atomic number tells us our number of protons, which is 92. And again, to balance it out, because it has no charge, we're going to go with an equal number of negatively charged electrons, which is why, again, it has no charge. And our number of neutrons in this case, going to be 238 minus 92. Feels like a lot, like a 146er, maybe something like that, give or take. Any questions on any of those there? Yeah. That would actually be exactly what it means. Yeah. So, and we'll talk about it after we do another example. But if something does have a charge, the only way for it to get a charge, right, is actually you would have to play with the electrons. So if it did have a -1 charge, like you said, that means it has one more electron than proton. So it's got one more negative charge than positive charge. So that's where the negative charge comes from. And we know it's the electrons, as we'll talk about maybe next time. But as we know, it's the electrons because if I change the protons, what happens? Is it the same element at that point? It is not. So we can't touch the protons. Otherwise, we do change the element. And since neutrons have no charge, it really is those electrons that are the only thing that would affect the charge. And just like if somebody had a positive charge, that would mean that it actually has less electrons than protons. So it has more positive than negative charges in that case. Other questions? We'll do some examples of that a little bit later on. So let's take a look at this one here. In this case, let's write the symbol with the mass number and atomic number. And again, the periodic table is your friend, but in case you can't see the big one on the wall, this is what you will see if you look over there. Yeah, let's take a look. So once again, as I mentioned, periodic table is really your friend when you do these. So we would go to the periodic table and find krypton, which is here. Again, we would write our symbol correctly, capital K, lowercase r. Also, the other important information we can get from the periodic table is our atomic number, which is up there on top. That should go bottom left. In addition to that, that also tells us that this guy, in terms of protons, should have 26. And that's important because we also need the mass number, which is our protons and our neutrons together. So we'll take 48 plus 26 will give us our mass number. And it looks like 84 in this case, which should go up there, up on top. Yeah. I probably did mean 36. Thank you. I think I got the math right. I just think I said the wrong number. Thank you. It is 36. There we go. Also helps to read the number correctly, I suppose. Yeah. I think 84 is good though on that. Looking at nitrogen, once again, we would go to periodic table if we weren't sure. And we could grab our 7, which is our atomic number and also our symbol, bottom left. That's telling us once again here, that's going to be 7 protons. So our mass number for this guy will be 6 plus 7, which is 13. And that would go top left there. And lastly here to finish up, iron, which is Fe. And again, that 26 that we could get from the periodic table is the atomic number. They actually give us the mass number here of 56. And that means in this particular guy here, the number of protons would equal the atomic number, which is 26. It is neutral, which means that it does need an equal number of electrons to balance out the charge. And our number of neutrons would be 56 minus 26, giving us 30 in this case. Any questions?